Welcome back to my channel InfoSec Lab. Today we're going to continue a series on TryHackMe's web app pen testing, and the topic is going to be HTTP Request Smuggling. In this room, you learn about HTTP Request Smuggling and its different techniques. It's a vulnerability that arises when there's mismatches in different web infrastructure components. This includes proxies, load balancers, and servers that interpret the boundaries of HTTP requests. For example, consider a train station where tickets are checked at multiple points before boarding. If each checkpoint has different criteria for a valid ticket, a traveler could exploit these inconsistencies to board a train without a valid ticket. Similarly, in web requests, this vulnerability mainly involves in the content length and the transfer encoding headers, which indicates the end of a request body. When these headers are manipulated or interpreted inconsistently across components, it may result in one request being mixed with another. Request splitting or HTTP desync attack. Request splitting or HTTP attacks are possible because of the nature of the keep alive connections and the HTTP pipelining, which allow multiple requests to be sent over the same TCP connection. Without these mechanisms, request smuggling wouldn't be feasible. When calculating the sizes of the content length and the transfer encoding, it's crucial to consider the presence of the carriage return, the \r, and the new line, the \n characters. These characters are not only part of the HTTP protocol's formatting, but also impact the calculations of the content sizes. While testing for request smuggling vulnerabilities, it's important to note that some tools might automatically fix the content length header by default. This means that if you're using a tool to run payloads, your content length values might get overwritten, potentially changing the test results. Note that testing for request smuggling can potentially break a website in many ways. Cache poisonings, some other user requests may start failing, or even the backend pipeline might get fully desynced. So extreme care should be taken when testing this on production websites. The objective of the room today is to understand what HTTP request smuggling is and its impact, how to identify HTTP request smuggling vulnerabilities in web applications, and how to exploit them. Also, we need to understand and apply the measures to mitigate and prevent these vulnerabilities in applications. Now, in order to start this room, there are going to be some prerequisites for the room, which is a basic understanding of HTTP 1.1 protocol and its headers. If you don't have any of this knowledge, I would recommend check out this room, which is the HTTP in detail. Here's the URL. We also need some familiarity with the web server infrastructure components like the load balancers, proxies, and the web servers. And of course, you need some basic understanding of Burp Suite. The importance of understanding HTTP request smuggling. Smuggle requests might evade security mechanisms like web applications firewalls. This potentially leads to unauthorized access or data leaks. Attackers can poison web caches by smuggling malicious content, causing users to see incorrect or harmful data. Smuggle requests can be chained to exploit other vulnerabilities in the system, amplifying the potential damage. Due to the intricate nature of this vulnerability, it can often go undetected, making it crucial for security professionals to understand and mitigate it. Okay. So we're going to deploy the target machine, and we're going to start our attack box, which I've already done so. The modern infrastructure. First, let's get to know the components of modern web applications. Modern web applications are no longer straightforward, monolithic structures. They're composed of different components that work with each other. Below are some of the components that modern web applications usually consist of. The frontend server. This is usually the reverse proxy or the load balancer that forwards the request to the backend. The backend server. This server-side component processes user requests, interacts with databases, and serves data to the frontend. It's often developed using languages like PHP, Python, and JavaScript, and frameworks like Laravel, Django, or Node.js. Databases, persistent storage systems where applications data is stored. Examples of these are databases like MySQL, PostgreSQL, or NoSQL. APIs, or applications programming interfaces. Interfaces allow the front and the backend communicate and integrate with other services. Microservices. Instead of a single monolithic backend, many modern applications use microservices, which are small, independent services that communicate over a network, often using the HTTP or the REST or gRPC. Load balancers and reverse proxies. Load balancers These devices or services distribute incoming network traffic across multiple servers to ensure no single server is overwhelmed with too much traffic. This distribution ensures high availability and reliability by redirecting requests only to online servers that can handle them. Load balancing for web servers is often done by reverse proxies. Examples include AWS Elastic Load Balancer, HA proxies, and F5 Big IP. Reverse proxies. A reverse proxy sits before one or more web servers and forward client requests to the appropriate web server. While they can also perform load balancing, their primary purpose is to provide a single access point and control for the backend servers. Examples include Nginx, Apache with a mod proxy, or Varnish. So we have the user, which is us right here, and when we send a request, the request will be sent to a load balancer or the reverse proxy. From here, depending on the logic of the application, it will forward the traffic to different servers that are available. And this server will communicate with each other and then send it to the backend resources. Let's talk about the role of caching mechanisms. Caching is a technique used to store and reduce previous fetched data or computed results to speed up the subsequent requests and computations. In the context of the web infrastructure, content caching, by storing web content that doesn't change frequently, like the images, CSS, and the JS files. Caching mechanisms can reduce the load on the web servers and speed up content delivery to users. Database query caching. Databases can cache the results of frequent queries, reducing the time and resources needed to fetch the same data repeatedly. Full page caching. The entire web pages can be cached, so they don't need to be regenerated for each user. This is especially useful for websites with high traffic. Edge caching, or the content delivery networks, or CDNs, cache content closer to the users at the edge of the network, reducing the latency and speeding up the access for users around the world. API caching. Caching the responses can significantly reduce the backend processing for APIs that serve similar requests repeatedly. Caching, when implemented correctly, can significantly enhance the performance and responsiveness of the web applications. However, managing caches properly is essential to avoid server stale or outdated content. It's essential to avoid serving stale or outdated content. Answer the questions. What sits in front of one or more web servers and forward client requests to the appropriate web server? Is reverse proxy. Behind the scenes. Let's take a look at the HTTP request structure. Every HTTP request comprises two main parts, the header and the body. As you can see right here, number one is the headers, number one, number two, and number three right here. The request line. The first line of the request, post admin login HTTP 1.1, is the request line. This consists of at least three items. The first one is the method, which is get or post. In this case, is post. The method is a one-word command that tells the server what to do with the resources. The second is a path component of the URL for the request. In this case, it's going to be the admin/login. The path identifies the resources on the server. Lastly is the HTTP version used for the application, HTTP 1.1. Now keep in mind that HTTP 1.1 and HTTP 2 have different structures, which we'll explore later. The request headers. These are going to be the request headers. Number two is right here. We have the host header, we have the content header, we have the content type, user agents, and transfer encoding headers. We'll dig a little bit deeper into the content length headers and the transfer encoding headers in this room. This section contains metadata about the request, such as the type of content being sent, the desired response format, and the authentication tokens. It's likely the envelope of the letter, providing information about the sender, receiver, and the nature of the content inside. Number three is the message body, which is the actual content of the request. The body might be empty for the GET request, but for the POST request or the PUT request, it could contain form data, JSON payloads, or the file uploads. So let's talk about the content length header. The content length header indicates the request or response body size in bytes. It informs the receiving server how much data to expect, ensuring the entire content is received. In this case, the content length is 14 bytes, meaning that the request or response body contains 14 bytes of data, which you can see right here. Transfer encoding header. The transfer encoding header is used to specify the form of encoding applied to the message body of a HTTP request or response. A commonly used value for this header is junked. This indicates that the message body is divided into a series of junked. each preceded by its size in hexadecimal format. Other possible values for the transfer encoding header include compressed, deflate, or gzip, each indicating a different type of encoding. For example, in this case, we have the transferring encoding values equals to chunked, meaning the B in hexadecimal equivalent to 11 in hexadecimal. So for the transfer encoding headers, we have three parts. The first one specifies the size of the chunk, which is right here, 11, and then this is the actual data or the content of the post request, and this signifies where the request should end. So how headers affect the request processing? Headers might play an important role in guiding the server to process the request. This is because they determine how to parse the request body and influence caching behaviors. They can also affect authentication, redirection, and other server responses. Manipulating headers like content length and the transfer encoding can create vulnerabilities. For instance, if a proxy server gets confused by these headers, it might not properly distinguish where one request ends or another starts. HTTP Request Smuggling origins. HTTP request smuggling primarily occurs due to discrepancies in how different servers interpret HTTP request boundaries. For example, if both content length and the transfer encoding headers are present, ambiguities can arise. Some components prioritize the content length, while others prioritize transfer encoding. This discrepancy can lead to one component believing the request has ended while another thinks it's still going, leading to smuggling. So for example, suppose a frontend server uses the content length header to determine the end of the request, while a backend server uses the transfer encoding header. An attacker can craft a request that appears to have one boundary to the frontend, but a different boundary to the backend. This can lead to one request being smuggled inside another, causing unexpected behavior and potential vulnerabilities. Answer the question, what request header indicates the request or response body size in bytes? This informs the receiving server how much data to expect, ensuring the entire content is received. That's content length. Okay, request smuggling in CL.TE. So what's CL.TE? CL.TE stands for Content Length Transfer Encoding. The name CL.TE comes from the two headers involved, the content length and the transfer encoding. In the CL.TE technique, the attacker exploits discrepancies between how different servers prioritize these headers. For example, the proxy uses the content length to determine the end of the request, and the backend server uses the transfer encoding header. Because of this discrepancy, it's possible to craft ambiguous requests that are interpreted differently by each server. For example, imagine sending a request with both content length and the transfer encoding headers. Frontend server might use the content length header and think that the header and the request end at a certain point due to the provided number of bytes. In contrast, the backend server relying on the transfer encoding header might interpret requests differently, leading to unexpected behaviors. So let's try to exploit this vulnerability. To exploit the CL.TE technique, an attacker crafts a request that includes both headers and ensuring that the frontend and the backend servers interpret the request boundary differently. So this is the payload right here. In this case, we have both the content length and the transfer encoding headers. So the front end will look at the content length headers and it says, oh, it's 130 bytes. Everything will be sent to the backend server. However, the backend server will take a look at the transfer encoding, which is chunked. And if you remember, number 0 signifies the end of the body. So the backend server will take a look at this one and say, okay, the transfer encoding is chunked and then the size is 0, meaning that there's no actual data for this request. So the request will end here. And this will be interpreted as a new request in the backend server. Incorrect content length. When creating a request smuggling payload, if the content length is not equal to the actual length of the content, several problems may arise. First, the server might process only the portions of the request body that matches the content length. This could result in a smuggled part of the request being ignored or not processed as intended. To make it easier to understand, let's take a look at this one. We have the content length of 24, meaning that it will take everything. So we have username is 24 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember 10 right here? 11, 12, 13, 14, all the way to 24, right? Because we specify the content length to be 24, everything will be interpreted by the backend server. Hence, it will show test, which is correct. Now, imagine we change the content length values to 10. It only takes all the ways up to this T, the first T right here. meaning that whatever behind this T will not be interpreted by the backend server. Hence, we get name is T in a query because nothing is interpreted, it's empty. Basically, that's what it is. So what does CL.TE stand for? Content-Length Transfer-Encoding. Request Smuggling TE.CL. So this is the opposite. TE.CL stands for Transfer Encoding Content Length. This technique is the opposite of the CL.TE method. In a TE.CL approach, the discrepancy in header interpretation is flipped because the frontend server uses the transfer encoding header to determine the end of the request, and the backend server uses the content length header. Similar concepts, but this time the frontend uses the transfer encoding header, whereas the backend uses the content length. So how do I exploit that? To exploit the TE.CL technique, an attacker grabs a specially designed request that includes both the transfer encoding and the content length headers, aiming to create ambiguity in how the front-end and the back-end servers interpret the request. The same concept, we have to include both of the headers. In this case, because the front-end uses the transfer encoding, we have to focus on this one first. Transfer encoding with a chunk right here. And then the size of this chunk is going to be 78 bytes, and this signifies the ends of the chunk. So the front-end will send everything here to the back-end server. However, because the backend server uses the content length to determine the body, it will stop right here because the body is only 4 bytes, meaning whatever here will be ignored. And because of that, this will be treated as a separate request in the backend server, leading to the vulnerability. The smuggle request is processed by the backend servers as if it were a legitimate separate request. This request includes the isAdmin true, which could potentially elevate the attacker's privileges or auto data on the server, depending on the application's functionality. So answer the question, what does TE.CL stand for? Transfer encoding and content length. Transfer encoding obfuscation. Transfer encoding obfuscation, also known as the TET, stands for transfer encoding transfer-encoding. Unlike the CL.TE or the TE.CL method, the TET technique arises when both the front-end and the back-end servers use a transfer encoding header. In the TET technique, the attacker takes advantage of the server's inconsistent handling of the transfer encoding present in the HTTP headers. The TE.TE vulnerability doesn't always require multiple transfer encoding headers. Instead, it often involves a single malformed transfer encoding header that is interpreted differently by the front-end and the back-end servers. In some cases, the front-end server might ignore or strip out the malformed part of the header and process the request normally, while the back-end server might interpret the request differently due to the malformed header, leading to request smuggling. For example, an attacker manipulates the transfer encoding header by including chunk in the malformed variations. This is done to exploit the front-end and the back-end servers prioritize the transfer encoding header over the content. By corrupting malformed transfer encoding headers, the attacker aims to make the servers to ignore the transfer header and use the CL instead, leading to a discrepancy in how the request boundaries are interpreted between the front-end and the back-end servers. This manipulation can result in either a CL.TE or a TE.CL situation, depending on which server falls back to using the content length. Exploiting the TE.TE for request smuggling. To exploit the TE.TE technique, an attacker may grab a request that includes the transfer encoding headers that use different encodings. For example, this request will have 2 transfer encoding chunks and chunk number 1. The first one is a standard chunk encoding, but the second one, chunk 1, is non-standard, depending on how its configuration. Front-end server might process the request based on the first transfer encoding chunk header and ignore the malformed chunk 1, interpreting the entire request up to the 0 as the single chunk message. Backend server, however, might handle the malformed transfer encoding chunk number 1 differently. It could either reject the malformed part and process the request similarly to the front-end server, or interpret the request differently due to the presence of a non-standard header. It is processed only by the first 4 bytes. If it only processes only the first 4 bytes, as indicated by the content name, the remaining part of the request started post-update is then treated as a separate new request. This could lead to unauthorized actions or data modifications, depending on how the server's functionality and the nature of the update endpoint. What does the TE.CL stand for? Transfer encoding, transfer encoding. Let's get to the exercise. The vulnerable environment has the ATS, which is Apache Traffic Server, as a front-end proxy, NGS as a web server backend, and the PHP processing the dynamic content. Due to the differences in how the ATS and the NGS prioritize the content length and the transfer encoding headers, there's a potential for the HTTP request smuggling. Start by adding this one to the host file. Okay, copy this one. IP address. Okay. This one, I believe. Let's double check. Looks like it's been added to the host file. Let's copy this one and open the web browser. Accessing the application. The web application in this room uses the link HTTP Request Smuggling at TCM. It features a home, login, and a contact form that enables the user to access and send feedback to the developer. For demonstration, the submitted queries are saved to the submissions directory. Below is a screenshot of the application. So let's try that. Oops. There we go. So let's try test query. Query has been saved. Okay, so we see our feedbacks right here. Cool. Let's go to the home page. Exploiting the application using Burp Suite proxy. Intercept a request sent to the web server's index. This request will become the baseline we will use to exploit the vulnerable application. Send the request to intruder and copy-paste the below payload. And copy-paste the below payload to the payload position box. Let's break down the payload. In the CL.TE vulnerability, since the proxy or the front end prioritizes the content length header, 160 bytes of the body is assumed to be the body of the first post, which is this one. The first post. The front end thinks that this is a single request and forwards it into the pipeline, where the backend server now prioritizes the transfer encoding, ending the first post request at the first size of 0, which is this one right here, assuming that the second post is a different request. So basically, the front end will consider this as a whole request, whereas the backend will consider this as 2 separate requests. So the payload positions box is going to be this one, the query right here. And we go to the payload tab. The payload tab is going to be no payloads. Subsequently, on the payload settings, we should generate 10,000 inputs. And on the resource pool, we have to clarify the maximum concurrent request, which is 10, and the delay between the two requests is going to be 2 seconds with random variations. And after that, we can start the attack. All right, let's try that. Let's go copy this payload right here. We at the applications index page. Intercept on. Turn intercept here. Go. Now this one was sent to intruder. Then paste the payload here. And this one is going to be our payload. Let's clear all the payload. Payload type is going to be null. And we need to generate 10,000 payload. We don't have to process the payloads or anything. So let's go to resource pool. Create a new one. Maximum concurrent request is going to be 10. We need delay between the requests, which is a mixed variations up to seconds. And start. Okay, so what does it do? After a few minutes, we should check the submissions folder to see if the request is smuggle containing requests of other users. We go through the text files and check the password that was appended to the query parameter, which is right here. And we can use the password to log in, retrieving the flag. Conclusion. HTTP request smuggling occurs due to differences in interpreting request headers by servers, mainly through the manipulations of the content length and the transfer-encoding headers, leading to unclear request boundaries. This can cause servers in environments with both front-end and back-end components to incorrectly define request limits, potentially allowing security bypasses and unauthorized data access. Mitigation approaches. There are several ways we can do. Uniform header handling. Ensure that all the servers handle headers in the same manner to prevent smuggling opportunities. We should also embrace HTTP version 2, which is implemented to enhance the management of the request boundaries, reducing the risk of smuggling. Ongoing surveillance and review is the third approach, where we should keep an eye on the server traffic for smuggling signs and perform periodic checks to maintain secure server setups. Last but not least, we should also educate our teams to raise their awareness, making sure that both development and operation teams understand the dangers of request smuggling and the preventive measures. To summarize, despite the significant risk posed by the HTTP request smuggling, it is a manageable issue with the right knowledge, strategies, and resources. Emphasizing security in web application development and management is crucial for protecting both the applications and its users. Okay, there's the questions, and let's go back to the exercise and retrieve the flag. So here comes the question. How long should we wait for the attack to run? We're not sure, but probably around 40 or 50 requests. I'm not sure. But let's just wait for about 50 requests made to the servers. Let's cancel the attack right now. I think it should be enough. Let's go back to the application and see what we get. So we go into submissions folder, and we see a ton of requests right here. Let's take a look at it. And we see the login password right here. Cool. Let's try this one. And we locked it. Here comes the flag. Here comes the flag. All right, that's it for the room today. I hope you enjoyed the room. And if you have any question about this vulnerability, feel free to reach out or put a comment below. I'll be happy to answer and help you. Thank you very much, and I'll see you next time. Bye.